Well, yeah, it's too late now because for the people who aren't here. But if you're looking for the videos, it's on the live tab. So there it is. All right, any issues with my algebra? Algebra look good? Okay, now we identify R. So my R here is negative 8x squared. I don't remember if this is exactly how we did it, doesn't matter. And then now we're going to rewrite this as an infinite sum. N goes from 0 to infinity of r to the n. And so the r there is negative 8x squared. So there's the next step. Stop me if I get something wrong, though. Because, yeah, we're coming down the home stretch here, and so my mind is elsewhere. Well, not really. It's here with you, mostly. All right, onward. Okay, so now I'm going to rewrite this like this. Negative 8 to the n times x to the 2n. One more thing, and this is because WebAssign doesn't like that x out front, I don't think. Let's move that x inside. I'll take my time with this. So this is going to be this. Negative 8 to the n, x to the 2n times x. And you can just combine exponents now. That's x to the first. So I think this is what WebAssign is going to want. We're going to find out. X to the 2n plus 1. Next, interval of convergence. Let's go down here. You remember that R originally was negative 8x squared. And you want R to be less than 1. And so I want negative 8x squared. Whoops. Be less than 1. Drop the negative. 8x squared is less than 1. X squared, I know I'm taking my time, is 1/8. That means x is less than 1 over square root of 8, 1 over square root of 8. Okay, I might have skipped one step there. Does that look all right, the interval? And because this is a power series, you don't have to worry about the endpoints. Oh, no, I'm sorry. Because it's geometric. Geometric, you don't worry about endpoints because you know that this doesn't converge at endpoints for geometric. All right, let's check it out, see if I'm right. See if I can be happy. Where's web? Assign me some webs. All right, I'm just going to copy this in just to see, because I like to see the little green check mark or whatever it is. There it is, negative 8 to the n. Negative 8 to the n times x to the 2n plus 1. Let's see, and then the interval as interval notation. So this is going to be 1 over square root of 8. Sorry. Forgot my negative. Comma. Done. All right, submit. Let's see if it's right. What was that, 4? Oh, green check marks, so happy. All right, hopefully that cleared things up. You'll notice that the homework near the tail end here is, I guess that at some point in the past, I was like, this is hard stuff. So I started at some point at the end just pushing it out to like the afternoon. That way you could figure it out and then fix it. That way you don't have to ask for an extension. So do it for class though. All right, anything else? We're good? All right, let's do the quiz. Yeah, it's on the list. Sorry. So there is a quiz. Now I should say though that I have a stack of papers in my office. I don't know what happened. Actually, I do know what happened. I went to Boston and that was lovely, but it kind of got me behind because I wasn't really doing my work that whole weekend. And so now I've still got this stack. And so I've decided I'm not going to collect anything, if I can help it, until that stack has gone away. So what we'll do is we'll have this quiz, and then you'll grade the quiz. And then I'll just assume that everyone knows what they're doing, and I'll put 100 on this quiz to transfer to the gradebook. But that doesn't mean you shouldn't try. So try it because this is good practice for the test later this week. There's too many, but you guys can share in the back. There's too few, and that's just one. Yeah, there it is. That's all right, I got it. I'll come get that. Thank you. Let's see, quiz A. There it is. Oh, can't see it. Looks like a number of people are done. But if you aren't done, don't panic. For one, I'm not collecting this. But for two, I'll give you another 30 seconds or a minute, maybe as long as it takes me to go fix that clock back there. Is that right? It's not off by 3 minutes like it was a minute ago. It's there. Yeah, let me know, Tony. Oh, oh, 6 seconds. Oh well, good enough. Good enough for me. Okay, so let's go ahead and take a look at this. Here we are. Here's the first one. This one isn't too difficult because you already have it as 1 minus x squared in the denominator. So you're like, oh, r has to be x squared. And I just don't like the 5. So pull the 5 out. And then you get this. That one's pretty straightforward. X squared has to be between 1 and -1, which means x is between 1 and -1. So hopefully that's not too shocking. I hope you all got that one correct, but if you didn't, hopefully it's just something like, oh, I left out a negative, or oh, I just, find your mistake. You found your mistake? No, it's x squared. This here, you mean? Well, okay, so, yeah, no, it shouldn't. So here's the geometric series that we're using, just to remind you. Yeah, so here's the r to the n is equal to 1 over 1 minus r. Yeah, so if you had something like this, here, I'll do it the other way. Yeah, just to clear this up. No, it is confusing. The backwardsness of it is that if you had 1 over 1 minus x, that's going to equal this, and equals 0 to infinity of x to the n. And then if you had 1 over 1 plus x, that's where you have to do the double negative thing. And equals 0 to infinity of negative x to the n. So yeah, so just yeah. There's certain places in mathematics where it's like you feel like you're going backwards or doing the opposite, and this is one of those. So because the geometric series formula has a minus down there to begin with, and this here is positive. But yeah, other than that, any other complaints, questions? All right, very good, good. So you can give yourself, just correct whatever you have, and then I'll just, that's fine, just put a big plus 10 or whatever it is you want to put up there. And then this next one, a little bit harder. So let's walk through this a little bit more carefully. First thing I had to do, I did this in stages. So the first thing I knew was that I didn't like the x up there, so I pulled it out. And I didn't like the 4, because that should be a 1, so I pulled the 4 out, but that left me with an x squared over 4. Because 4 times x squared over 4 is x squared. 4 times 1 is 4. That's the first step. Just don't even look beyond that. If you're confused, make sure that step works. If it doesn't, now's the time to ask. Then I did a little rearranging. So I moved the 1 out front, and then I took that and did the double negative thing. And that helped me to see that r was equal to x squared over 4. Then I put that down here into that geometric series. And then I rearranged a little bit. I know I did a bunch of stuff in one step. Let's see, I separated out the negative. So negative 1 to the n. I took that x squared to the n and made it x to the 2n. I took the 4 to the n, made it 4 to the n. And you might say, well, where'd the extra 4? Well, that came from here. I pulled that in. So it's 4 to the n plus another 1. So that's 4 to the n plus 1. I guess it's 4 to the n times 4. and that gives you this. Same thing goes here with this x. When I move it next to the x to the 2n times x, you get x to the 2n plus 1. So anyway, there's my series. Yours might have looked a little different, but it should basically be the same idea. If you put your if you left the 1/4 out front, that's fine, but you should definitely move the x inside the summation to make it, make WebAssign happy. And if WebAssign's happy, then I'm definitely happy. So I'm generally a little less hard on you than WebAssign. I don't know if you noticed, I hope. Okay, next we need the interval of convergence. That's easy enough because you have that radius of convergence there. So that thing goes inside here, which gives you this. Oh, sorry, this isn't radius. This is the interval of convergence. And I just looked ahead at the homework. The radius of convergence is 2 because you're starting at 0, you go 2 units on either side. -2, +2, radius is 2. Today's homework you're going to have when we get to the, oh, I forgot to write it, homework preview. We'll get there. All right, so any other complaints or questions about this one? This one was hard. Hopefully, I mean, maybe it was easier for you because of the plus. Apparently that one made it too easy. It became hard. Okay, so what we're doing today is we're going to figure out how to make a power series for any function at all. So for example, let's go down here. Let's say that I have this function, f of x is equal to, how about the square root of x plus 4? It's to make it easy on myself. So what I'd like to know is, what is the power series representation of that? Now, the thing about this function is that this function does not fit the geometric series. And so we're kind of stuck now. But we can use some math, some tricks, some math to make a series here. So the trick is that we're going to use what's called a Taylor series. So let's write down, I got PowerPoint, but I've already got this written here. So I'll pull up the PowerPoint in a minute. So Taylor series, that just refers to a power series for a generic function. A way, hold on a minute. Sorry, I should have put the word, should have changed this. A way to write a power series. There we go. That makes me feel better. So what you can think of is, think of Taylor series as just being a method, a way of coming up with a power series for any function. And when I say any function, I mean, okay, almost any function. That's what I mean by this. Yeah, what do you think? Oh yeah, good question. Why would we care? Well, let me write down an example where we would care. So that one is not a good example, but this one is a good example, e to the x squared. So this is a piece, I put this up here before. This function is part of the normal distribution. If you look at the formula for the normal, sorry, now it is. If you look at the formula for the normal distribution, which is the foundation for all of statistics, that is part of that, the expression for the normal distribution, e to the negative x squared. And to do work with statistics, you have to be able to integrate this function. Unfortunately, though, this does not have an elementary antiderivative. There is no antiderivative for this. However, it does have a power series. And so one way to accomplish this, to find the area underneath that curve, is to use the power series. So there are some reasons. For now, you can think of it as just a game. So we're going to solve a puzzle, solve a game. But there are reasons like this. Another good reason is to, oh, this is a good reason for you guys, is to get a computer to do calculus for you. Oftentimes, you have to rely on the Taylor series expansion for a particular function. And that allows you to get the computer to do the calculus for you. So anyway, that's another reason. But you can take numerical methods to learn about that. Okay, but getting back to this, let's find this way to write a power series for a generic function. So let's see, how do we want to do this? Do you want to just see the formula or do you want to see the y? Both. Let's do the formula first. Formula first? Formula. So the formula is this, and this is going to look pretty ugly, but don't fret. It will make sense maybe. So let's do this. The sum where n goes from 0 to infinity of f in, I'll explain in a minute, of 0 over n factorial times x to the n. There we go. Let's just write that as x to the n. Just a minute. X to the n. Okay, first let me explain this, and then we'll see why, the why. So this is just a brilliant way to do this, is basically you're just, well, here, let's find out why first, and then we'll find out what it all means, then we'll do the why. So what does this mean? That there, f in of x is the nth derivative. Of f. So that's the notation. I know it looks like you're raising it to the power of n, but what are we going to do? We want to say we're doing the nth derivative of x, of f, with respect to x. Okay, the next thing, just to note, in factorial, you all know what that means, I hope. It is in factorial. But the only reason I wanted to pull that out is to point out that 0 factorial is equal to 1, which is, I know, confusing and irritating. Do I have to explain why that is? Okay, without getting into combinatorics, let me explain it this way. 5 factorial is 120. True? Yeah, 5 times 4 times 3 times 2 times 1, 120. 4 factorial is 24. 4 times 3 times 2 times 1 is 24. You got this? We're all on the same page? What about 3 factorial? Oh, that one's easy. It's 6. 3 times 2 times 1. Okay, 2 factorial is equal to 2. It's the easiest one, and I'm having trouble. Yeah, 2 times 1 is 2. What about 1 factorial? That's 1. Yeah, it's just 1. What about 0? Oh, yeah, what is 0 factorial? Well, one way you could do this is you could say, hey, when I go from 5 to 4, I divide by 5. So 120 divided by 5 gives me 24. And then to go from 4 to 3, I probably should have put my division symbol elsewhere. Let me put it over here. You divide by 4 here, 5. Then you divide by 4 to get the next one. Then you divide by 3, divide by 2. So I'm kind of working my way backwards. So then you divide by 1. Why not? I mean, it follows the pattern, doesn't it? So what is 0 factorial? It's 1 divided by 1, which is 1. Okay, so you might say, well, let's go the whole distance and find negative 1 factorial. Sure, we can do that. Negative 1 factorial, divide by 0. Oh, undefined. And negative 1 factorial is undefined. So 0 factorial is defined. It's 1. Negative 1 factorial doesn't exist. So that's why you don't have negatives, but you do have 0 factorial. So there you have that. Okay, now let's actually do this. Oh, the why. Why is this the way it is? Okay, well, let's check. Let's see if we can figure out why this is the way it is. First of all, let's imagine doing what is f, hold on a minute. So f of 0 is what you get when you plug 0 into all of this. Okay, well, that's going to be f of 0 over 0 factorial times 0 to the 0th. Well, x to the 0 is 1, so we're just going to put that there. 0 to the 0 is not 1, but we're going to put a 1 here, plus f prime of 0 over 1 factorial times 0 to the 1st, plus f double prime of 0 over 2 factorial times 0 squared, etc., etc. Now that explains why f of 0 equals the summation. You can see all the zeros are going to be 0. Everything is going to be 0 except for this first term. But what about another number like f of 1? Why would f of 1 match up? Well, I'm not sure that it does, I should say. This is a power series. All I know for sure is that it's going to match up for 0. I don't know about 1 because it may or may not be in the interval of convergence. So you'd have to work on that one. But I can say this, that f prime of 0 is what you get when you do the derivative of this. And first of all, let me do f prime of x. So do the derivative of this, and you get the sum, where n goes from 0 to infinity, of f n of 0 over n factorial times n x to the n minus 1. So anyway, that's what you get. And when you plug 0 into this, f prime of x, using that formula, you actually get f prime of 0. You see this f prime of 0, because you're multiplying it by 0 to the 0, you end up with f prime of 0. Okay, almost done with my explanation of why this works. And I know this isn't a complete proof, but you don't want a complete proof. You just want to get a general idea. So we have the slope. The slope matches, f matches, the function matches. And so imagine what's happening here is you have this matching at the point. So let's do this. This is 0 and f of 0. The slope matches. And so in a sense, if you ignore all of the rest of the terms, what you have here is you have the linearization for this function. And so if in fact this does converge at 1, that linearization is going to be close to f of 1. That doesn't prove that it's equal to f of 1, but it's close. All the other stuff that I crossed out up here, I'm waving my hands a bit, but this, the rest of the stuff would actually bend this to be wherever f of 1 was. So this is the linearization, back from Calc 1, the linearization at 1. The actual function may be right there, and all those other little terms, all of these are going to pull it. Without showing you all the proof, it does pull it down. What I wanted to do for sure, though, is to show you how. How do you get a Taylor series expansion? So here's what we're going to do is we're going to find the Taylor series expansion for that function. So let's go down here. Here's how I would suggest you proceed. This is going to be very formulaic, which I know you guys love. Formulaic answers, don't you? So step 1, make a table. That table is going to have 3 columns. You're going to have n, you're going to have f n, and then you're going to have f n of 0. Then you start filling in the table. Start with 0. Hopefully no one had any problems with that. Sadly, we have to do the derivative of that. Let's see if we can find a derivative person. In fact, we're going to do several derivatives, so don't fret. You're going to get to do your derivatives if you want to. Sorry, got distracted by notifications. It's terrible. Okay, so where are we? Who is this? Sean, not here. I'm sure he could do it though. Lucas is here. Do you know the derivative of x plus 4, square root of x plus 4? Is that right? So times 1, chain rule. So you're correctly doing the chain rule, but there it is. By the way, if you're confused about where Lucas got his x plus 4 to the negative 1/2, here's where it came from. This square root of x plus 4 is this. All right, let's go ahead and plug in 0. So let's see, that's going to be 1/4. Is that right? When I plug 0 into that, double check my math. If you need to, pull out your calculator. Okay, number 2. All right, here we are. All right, Briar, you're up. Can you do the derivative of that thing there? And then, of course, times 1 because of the chain rule, but yeah, it just goes away. All right, can I do this? I can do it. That's going to be negative 1/32. You can double check my math if you don't believe me. You'll get about negative 0.034, whatever it is, but there it is. Is that right? You think? Sure. Yeah. Oh, some people don't though. So thank you for reminding me that I do have some unbelievers. So here, I will do that one. I will do that one in full. It's negative 1/4 times 0 plus 4. Sorry, not square root, to the negative 3/2. So that's all I'm doing to get this negative 1/32. So if you're wondering where did it come from, you have two options at this point. Punch it into your calculator. That's the not so cool version. The cool way to do this is to actually work it out. Negative 1/4. Let's see, I'm going to do this 4 to the 3/2. And that's going to be negative 1/4 times the square root of 64. Because 4 to the 3/2 is the same as 4 cubed, and then you do the square root. And we all know the square root of 64. 4 times 8, which is 1/32. How's that? It's not bad, is it? Sure, that's good. Okay, so that's that. Let's do one more, and then we're going to give up. Well, no, we're not giving up. We're just going to move on to the next example. Tony, do you know the derivative of that thing? So 5/2. Excellent. Now I'm going to plug 0 into that. Let's see if I can do that in my head. 32 and 8, 32 times 8, that's 2 to the 5th times 2 to the 3rd is 2 to the 8th. So that's going to be 3/256. Does that look all right? Yeah, all of you binary people. Binary? That doesn't sound right. All of you computer lovers. I don't know. Yeah, zeros and ones, right? You should know your binary. Okay, but anyway, there it is. Okay, so where is this going? Now what we're going to do is, sadly, this one, I don't see a strong, there is a pattern, but the ultimate thing would be to find a pattern, which I'm not going to do for this one. We'll do for the next one because I chose poorly for this first example. So we're not going to do the pattern for this one. We're just going to write down the first few terms of this particular Taylor series. So this is going to equal, starting off with 2. So that's the first number here. I won't bother with the rest of it. It's always just that first number. And then plus 1/4 times x. Then minus 1/32 over 2 times x squared. Then plus 3/256 over 6 times x cubed. Okay, so what am I doing here? I've got the first number. You just got that right there. The second number is always times x. The third number gets divided by 2 factorial. 2 factorial is just 2. And then the fourth number ends up being divided by 6. You would continue in that fashion. Sadly, there's not a strong pattern here. I was hoping there was something I could, oh, wait a minute, can I exploit this? 3 cancels with 6. Maybe I can. Because this is, let me write it out. So this is going to be 2 plus 1/4 minus 1/64 plus 1/512. Oh, sorry, the x, sorry, I was looking at the sequence. Ooh, because this is 2 squared. And then, let me see, this is going to be 2 squared. And then this is 2 to the 6th. And this is 2 to the 9th. No. I was excited. I thought that there would be some pattern with the powers. I'm guessing the next one's going to be negative. I don't know exactly what it'll be. So we'll just leave it at that for now for this one. there is probably a pattern that I'm not seeing right off the bat. I'll show you one that has a very obvious pattern. I hope it's obvious. We're going to see. So let's try arctangent. I know, you know it's one of my favorites. So let's start with arctan. And so make your table. That's step one. In, F in, and then F in of 0. Okay, so F in of X, arctan, starting out. And then I'll do this one for you. The arctangent of 0 is 0. Now we need to do some derivatives. You can do these. Gina, you know the derivative of arctan, don't you? And I'm just going to rewrite this to make it easier for the next person. So those are both the same. Let me plug 0 into that just so that you can see that I can do it. Very nice. All right, let's get the next one. All right, Haven, you know the derivative of x squared plus 1 to the negative first power, don't you? Oh, sorry. I didn't quite hear you. There, -2, okay? And then what else? Chain rule. Yeah, put an X there. Yeah, so it's a little jumbled, but yeah, so you do -1 times this to the -2 times the derivative of x squared, which is 2x. Sorry, they got separated in my mind. I think Haven said the 2 and then he corrected it, but I didn't bother fixing it because I knew we would use the 2 eventually. But so that's the second derivative of arctan. Now we're going to plug 0 into that, and you get 0. Well, that's not very exciting. But the next thing is, so let's see if we can conquer the next one. One more derivative, and then we'll see where we are. Marissa, you think you can do it? Do you want me to write that as a quotient, or do you want to do the product rule? The chain rule. All right, just a minute. Haven's going to help us out then. So here, Haven actually spoke the chain rule correctly. So let me back up then to here. The derivative of this thing, Haven said, was going to, you subtract 1 from the power. So you got that part right. You multiply by the power, the original power. So that part's okay. The chain rule says, after you do that, you have to multiply by the derivative of what's in the parentheses. So that's my fault that I didn't write it out like that, but that's what Haven said. And so that's the correct derivative there. I'm just going to clean it up a bit. And then you get this, x squared plus 1 to the -2. So that's the second, that's this one. Now we got to do third, which is going to be a pain. So do you think you can do it? You want me to help you through it? Yeah, let's help you through it. So we're going to use the product rule because you have a product, and then we'll use the chain rule too. But let's do product rule first. So you got the -2x times that stuff. What's the derivative of -2x? -2. And then you leave all of this stuff alone. And then you add to that -2x times the derivative of all that stuff right here. So do exactly what Haven did, multiply by the -2. And then what power do I have up there now? -3, very good. And then I have to multiply by the derivative of what's inside the parentheses. So what's the derivative of x squared plus 1? 2x. And that's ugly, isn't it? That's a horrible, ugly mess. Let me clean things up. We have -2 times x squared plus 1 to the -2. Ooh. Is that going to be plus 8x squared? X squared plus 1 to the -3? Yeah, I think so. Anyway, if I plug 0 into this, you can plug 0 into this yourselves. You actually just get -2. Now this one as well is not a pattern that is going to be nice. Oh, no, it's a nice pattern, I should say. It's just that it's not going to be nice to find. I know what the pattern is because, like I said, arctan, favorite thing. Sad. Well, let's see. Let's do one that we can do. Let's take the one that's going to be your favorite. This one. I know, I keep switching on you. F of x. I should have stuck with the PowerPoint apparently. I just got excited about Taylor series. So try f of x equals x squared. So in, and then f in, and then f in at 0. This one you're going to love. So when n is 0, the function is e to the x, which makes this 1. Let's see if we can find a pattern. Oh, it's almost time to, no, yeah, we have 10 minutes. All right, Sarah, what's the derivative of e to the x? Very good. And let's see, Sydney, can you plug 0 into e to the x? What was that? 1, you said? That's what I thought. Okay, very nice. So you're just doing e to the 0 is 1. All right, next, do the derivative. Haven, what's the derivative of e to the x? Yeah, so you see why this is one of your favorites probably. You probably see a pattern already, but just in case, Cheyenne, what's the what do you get when you plug 1 in, or 0 into that? Yeah, 1 as well. I'll bet you can just guess what the next one is. Briar, what's the next line look like? Derivative, yeah, e to the x, and what's this number over here going to be? Yeah, so notice that these are all 1s. So that makes things so nice and easy. So now we can write the Taylor expansion for this. So just to note, you start with this number, and then you take the next number times x, and then the next number over 2 factorial times x squared, and then the next one over 3 factorial times x cubed. Can you see the pattern here? I'll bet you can figure it out from here. Anyway, the total, if you wanted to write this as a summation, you would do this. 1 over n factorial x to the n. And that's e to the x. Should have stuck with the PowerPoint, I think. Let me just see what well, it may be too late for that. What I do want to say is that we should modify this homework. Let me just view it here again. Yeah, that's no good. Yeah, I'll just, you know what I will do is I will push the homework back a day. It'll be all right. So it'll be due Wednesday. So here's the plan for the week. I've actually got it written down here. I'll read it to you. Monday, Taylor Series Part 1. Tuesday, Taylor Series Part 2. Wednesday, wrap-up review for Test 4. Friday, Test 4. Monday, next week, wrap-up review for the final. And then we're all done. So tomorrow we'll do Taylor Series Part 2. And I will just push the homework back so that you don't have to worry about it. And I'm doing that right now. So that way you can focus on your CAD presentations if you're one of those people. If not, you can go see the CAD presentations. Let me stop the recording, and then